An equilibrium constant is the product of molar concentrations of the products for a chemical reaction, each raised to the power of its representative coefficient. So if there's a 2 in front of the compound, i.e. 2 NaCl, the concentration would be raised to the power of 2. Divided by the concentrations of the reactants, each raised to the power of its coefficient in the equation. So it's products raised to the power of its coefficient over reactants raised to the power of their coefficient. So the question becomes, why do we calculate equilibrium constants? So why is this important? Well, it's important because sometimes we need to know. The ratio of products to reactants. To see which side of that equation is favored. So if it is very large, we know that the products are favored. If it is very small, we know that the reactants are favored. If it's 1-to-1, then products and reactants are equal. So there are some rules when we're determining equilibrium constants. Concentrations are always expressed in moles per liter. The product concentrations are always placed in the numerator, so on the top of the equilibrium law expression. The reactants are always on the bottom in the denominator of the equilibrium expression. And the powers to which the concentrations are raised are always determined by the coefficients in the balanced equation for the reaction. So now let's go over some examples. The following reaction occurs in a 500 milliliter container. So that is 0.500 liters. At equilibrium, there is 0.7 moles of ethene, C2H2. There are 0.8 moles of oxygen and 0.9 moles of CO2 and 0.5 moles of H2O, all in a 500 milliliter container. And then it asks us to write out this equilibrium law expression and then determine the equilibrium constant for this equation. Here's your big hint. First, calculate the molar concentration of each reactant and each product. So we know for, let me get another color, C2H2, I have 0.70 moles, and I am dividing that by the volume of the container, 0.5 0.500 liters to give me 1.40 moles per liter. Actually, it's only one significant digit, so I dropped that second zero. Now for oxygen, O2 is equal to 0.80 moles all over 0.500 liters, which should be equal to 1.6 moles per liter. For carbon dioxide, CO2, that is equal to 0.90 moles over 0.500 liters, which should equal 1.8 moles per liter. And lastly, water, H2O, is equal to 0.50 moles all over 0.500 liters, which should equal 1 mole per liter. Now I have to figure out which one of these are on the product side. So product, and which one are on the reactant. And now I'm just going to use two different colors of highlighters to remind us. Product side, CO2 and water. So this is a combustion reaction. And reactant side, ethene and oxygen. So now I'm going to set up my equilibrium law expression. Remember, I'm going to look at the coefficients, so we can often write a general reaction in this way. Little a, which is our coefficient to end A, plus b. It's an equilibrium equation, so I need the double-headed arrows. And then little c, big C, plus little d, big D, where these values are the coefficients. And these values are the compounds. So when I write my general equilibrium law expression, I write it in this way. Kc, so that's equilibrium, is equal to my reactants, my products, the concentration of compound C to the power of C times the concentration of D to the power of D, the square brackets always mean concentration, divided by my reactants. So the concentration of A to the power of A, the concentration of B to the power of B, where these powers are my coefficients, so the numbers in front, and these values are my concentrations of these particular compounds. So now all I do is I plug in my values. So in this case, Kc is equal to my products, which are water, 1.80 moles per liter, to the power of 2, because that's actually carbon dioxide, to the power, no, I was right. Oh, no, I wasn't. To the power of 4, because this is CO2, because 4 is my coefficient, and my coefficient for water is 2, multiplied by 1 mole per liter, to the power of 2, all divided by ethene is to the power of 2, and oxygen is to the power of 5. All divided by 1.4 moles per liter to the power of 2 and 1.6 moles per liter to the power of 5. When I do that calculation, you'll notice that my units should cancel out. So moles per liter cancels up and down. And when I do that calculation, I get a value for Kc of 0.51 with no unit. So for here, what this tells us is the Kc is close to 1. So there's about the same products and reactants. With the reactants, right, with those reactants on the bottom, slightly favored. These guys are slightly favored. So to recap, equilibrium law rules. What do you always include? You always include gases, and you always include aqueous solutions. What do you never include? You never include solids. So it's a green light for this, it's a red light for this. And then you sometimes include liquids. If there is more than one liquid, they are all included. If there's only one liquid, it is not included in the expression. So that means something like if all of the aqueous ions are dissolved in water. You would not include water. So now it asks us to list 3 properties of chemical systems in equilibrium. And so it has to be a closed system. Our macroscopic properties, so things that we can see, are constant. So recall, this means things like color or pH are all constant. And there has to be equal rates of forward and backward reaction. So why is this considered dynamic? It's because they go back and forth constantly. That's an and. They move between product and reactant constantly. That's the dynamic part. What is it meant that when we say the macroscopic properties are constant? So this means that the things that you can see or measure, so if you can see it, it appears as if there are no changes. Even though we now know that it's at dynamic equilibrium, we can't see it with our eyes or measure it with our devices. So now we're asked to define some terms. So constant means that it's not changing. Dynamic means constantly active or changing. Static means without motion or fixed. And the rate is the speed of change. So it's a ratio involving time. So here are some reminders of equilibrium questions. Only the concentrations of gases and substances in solution are written in an equilibrium law expression. A liquid alone in an equation is excluded from the expression, but if it contains several liquids in the same equation, that must be included. So for here, I have ammonia, I have oxygen, I have nitrogen gas, and water. They're all in gaseous form, so they're all included. If I were to write an equilibrium law expression, I don't need that. I would write it as products over reactants. So here I would write NH3 on the bottom to the power of 4, its coefficient, and oxygen gas to the power of its coefficient, which is 3. Then on the top, I would write nitrogen gas to the power of its coefficient, and water to the power of its coefficient. And that would be the equilibrium law expression for this equation. Now, this one's a little trickier. We have to look to see what we include and what we don't include. Recall, we don't include solids in equilibrium law expressions, so all of these solids are not included. So our equilibrium law expression just contains one substance, which is ammonia. So in this case, our Kc is equal to 1 over, because I don't have any products I can include, 1 over the concentration of NH3 to the power of 2, because that's its coefficient. Again, I'm going to look at the bottom question to see if I have anything I need to exclude. I have a solid, I exclude those, and now Kc becomes, in this case, I put all of my substances on top because they are all products. my Kc then becomes the concentration of CO2 to the power of 2 multiplied by oxygen to the power of 1. Like in math, anything to the power of 1 is the same, so I don't necessarily have to put it down, but I'm just reminding you that there's that imaginary 1 in front of oxygen. Okay, let's go over the next one. Here, I'm looking again to see what I exclude. Silver chloride is something that I can exclude. And so now I set up my equilibrium law expression. Kc, recall I put products on top. So sodium nitrate, NaNO3. Again, it doesn't have a coefficient in front of it, so we just assume that that 1 is imaginary over the concentration of NaCl. Again, to the power of 1, I'm just not going to write that. And silver nitrate to the power of 1. In our next question, I'm going to again look for what I can exclude. I don't have to exclude anything. Just to recall, here are my products, here are my reactants. So now I'm going to say Kc is equal to CO2 gas multiplied by H2 gas all over the concentration of CO gas times H2O gas. We're including this because water is in its gaseous state. Recall, I don't have to include liquids in my equilibrium law expression. So again, reactants, again, products, I'm crossing out water. So here Kc is equal to N2H4 concentration. It has no coefficient, so we're just assuming to the power of 1. Nope, that was wrong. It's the products that I put on the top. N2H5 times the concentration of OH minus. We're just assuming an imaginary 1 there because there are no coefficients, all divided by N2H4. For the next one, here are my reactants, here are my products. They're all gases except this is a solid. I don't include that in my equilibrium law expression. And I don't include that. So again, I have another one where I can just write the products. So the products go on top. So I have CO2 gas times water, gaseous water. And those don't have a coefficient, so I just assume that that's 1. For the next one, I'm making liquid water. I can cross out water. Here are my products, here are my reactants. So in this case, Kc, I just use that 1 as a placeholder. And I say H2 gas to the power of 2 times O2 gas, because I only have a 2 in my coefficient. Here I have multiple liquids, so I'm going to include all of those liquids in my equilibrium law expression. I have a product here and I have a reactant here. I know products go on top, so Kc is equal to C6H5Br, so it's a brominated hydrocarbon, multiplied by HBr all over C8 or C6H6. So this is likely to bring you back to our organic chemistry, that's likely a benzene ring, and you're doing a substitution to add a bromine to that benzene ring. So recall, you can do benzene with those 3 double bonds or a circle, and then we're just going to stick a bromine plus HBr is what you're getting at the end. So what you're seeing is a substitution, just for your information. That has nothing to do with the reaction, but it's just interesting that this is an organic example. So here we have another organic example. We have ethanol and acetic acid. And it's producing an ester. Ethyl ethanoate. Again, so this is an esterification reaction. Just for your interest. And so here we have the products and we have the reactants. So we're going to start with ethanoate. We're going to get rid of this liquid water. Actually, we're going to keep this liquid water because we're going to keep all of the liquids. This is a liquid, this is a liquid, this is a liquid, and this is a liquid. So we're going to keep that liquid water. So we're going to write ethyl ethanoate, C2H5, COOC2H5 times H2O, because there are no coefficients in this balanced equation, divided by C2H5OH times C2H5COOH. We're going to keep going over a few problems here. So this question says, at a temperature of 350 degrees Celsius, the equilibrium concentrations for this reaction are this. Calculate the value of the equilibrium constant for this reaction at 350 degrees Celsius. So remember, you can only calculate equilibrium for specific temperatures. So I'm going to figure out my products and my reactants. I'm going to set up my equilibrium expression. So Kc is equal to products, which is the concentration of NH3 to the power of 2 all over the concentration of N2 and H2 to the power of 3, because those are those coefficients. So in this case, my Kc is equal to 1.230 moles per liter to the power of 2 all over the concentration of N2, which is 0.885 moles per liter multiplied by 0.665 moles per liter, all to the power of 3, which gives me a Kc of 5.81 to 3 significant digits. So those are how you do that question. Sometimes they will give you Kc and they'll ask you to find an unknown. So because all of this is our liquids, again, this is our esterification. We don't know the concentration of water. We're asked to find that. So we have to set up our equilibrium constant equation to solve for water. So first we'll start this way. So Kc of ethanol, I'm just going to write the terms. times the Kc of acetic acid Kc is equal to products over reactants. So ethanol, I didn't leave enough room the last time, multiplied by acetic acid, again, no coefficients, all over water and ethyl ethanoate. This is our ester. So we're going to solve for water. So the first thing we're going to do is we're going to move all of these things to this side. So we're going to say Kc times ethanol and acetic acid is equal to water and ethyl ethanoate. I'm just going to do EE. So now I know I need to isolate EE by dividing both sides by water. So I'm just going to move water to the bottom here. So now I know that if I multiply Kc by ETOH ethanol and acetic acid, oh no, I'm isolating for water. I'm moving ethyl ethanoate to the bottom. And dividing that by ethyl ethanoate, EE, I can solve for water. So all I have to do now is sub in those values. So 2.2 times the concentration of ethanol, which is 5 moles per liter, and multiply that by the concentration of acetic acid, which is 0.10 moles per liter, all divided by the concentration of ethyl ethanoate, which is 2.0 moles per liter, should give me water, the concentration of water. And so the concentration of water should equal 5.5 moles per liter. So you can flip these formulas around, easy peasy, lemon squeezy.